Hello everyone. Today we'll learn about eigenvalues and eigenvectors, their derivation and their properties. We all know that matrix multiplication can be viewed as a linear transformation. That is, when you multiply a vector with a matrix, following transformation may take place. Either there will be a change in length or direction, or both length and direction, or there can be no change. Let's consider a few examples. If we have a matrix A 1 2 3 4 and a vector x1 1 comma 1, then after multiplication it becomes 4 comma 6. We can see this transformation in the graph. The vector 1 comma 1 becomes 4 comma 6. Similarly, if we have another vector x2 minus 1 comma 1, which is this one, then after matrix multiplication with a vector, a matrix, it becomes 2 comma 2. You can see the multiplication part here. In both these examples you will see that direction and length, they both change. However, there will always be vectors whose direction does not change after matrix multiplication. These vectors are unique to that matrix. Thus, the vector whose length changes after matrix multiplication are called as eigenvectors for that matrix. Now, by the term eigenvectors, what I mean, the term eigen means self or own. That means the transformation they undergo in themselves. Mathematically, we can write it as ax is equal to lambda times x vector, where a is a matrix, x is a vector, and lambda is a scalar value. Lambda is the scalar value by which the original vector changes length, also called as the eigenvalues. Now, solving this equation, we get ax minus lambda times x. Now x is a vector, therefore we need to scale it up. We can write lambda x as lambda times I times x. Now we get a minus lambda times I, the whole bracket multiplied by x vector. Now to perform this subtraction, we know that I is an identity matrix and it is a square matrix. Therefore we can say that A also needs to be a square matrix to perform this subtraction. Therefore we get A minus lambda times I x is equal to 0. Now we can write A minus lambda times I is equal to B. Therefore the equation becomes Bx is equal to 0. Now let's quickly recall few concepts. If we have a system of equation a11x1 plus a12x2 is equal to b1, a21x1 plus a22x2 is equal to b2, then we can write this system of equation in the matrix form as ax is equal to b. Here remember that this a is different from the a which we started with. I am just using this a to write the system of equation. Now elaborating further, when this constant term b becomes 0, then we get homogeneous system of equations. You can see when the constant term b is 0, we call it as homogeneous system of equation, and the equation becomes ax is equal to 0. Now if you substitute x as the 0 vector, then this equation will always be satisfied. So we call x is equal to 0 as the trivial solution of this equation, whereas when x is not 0, we call that as a non-trivial solution. In this particular video, we are particularly interested in the non-trivial solution because by definition we started with whose length changes after matrix multiplication. So we cannot consider the 0 vector because 0 vector does not have any length. Okay, now coming back to this equation, bx is equal to 0. Bx is equal to 0. We know that b is equal to a minus lambda I times x is equal to 0. Now let's solve this equation for a 2 by 2 matrix. For the above system of equations, we can write a as a11, a12, a21, a22, I as 1, 0. It's a 2 by 2 matrix. Therefore a minus lambda I will become a11 minus lambda, a12, a21 and a22 minus lambda. In some videos you'll often see that this is called as the characteristic equation, and the roots are called as the eigenvalues. So we get this system of equation: a11 minus lambda times minus lambda the whole times multiplied by x1 plus a12 x2 a21 x1 plus a22 minus lambda times x2 is equal to 0. Now we are particularly interested in solving for a non-trivial solution. That means we know that x bar is not equals to 0 vector. So if a vector is not a 0 vector, that means one of the entries has to be non-zero. So in this case our vector is a 2 by 1 vector. That means at least one of the entries is not 0. Therefore we can have either x1 as 0 and x2 as not 0. That means if x vector is equal to x1 x2, that means x1 cannot be a 0 whereas x2 can be a 0, or x1 can be 0 and x2 cannot be 0, or x1 and x2 both cannot be 0. Let's consider all these three cases one by one. Let's consider the first case. x1 is 0 and x2 is not 0. When this is the case, substitute these values in this equation. What do we get? After solving we get a21 as 0, a22 as lambda, a11 as lambda. That means the original vector a becomes lambda 0 0 lambda. Now pay attention to this matrix. Remember this matrix. What does this say? That when one of the entries is 0, then the eigenvalues are the diagonal entries of the matrix. Here one of the entries was 0, then the eigenvalues were the diagonal values of the matrix. Similarly, here we have x1 is not 0 and x2 is 0. Here also one of the entries is 0 whereas the other entry is not 0. Then again, after solving this equation, you can pause the video and look at the calculation. You can see that the eigenvalues will again be the diagonal entries of that matrix. Now solving for the, we'll come to this portion at the end, but now solving the third case where x1 is not 0 and x2 is not 0, you can pause the video and look at the calculation. You can see that this is what we get at the end. This is what we get at the end. And what is this? This is nothing but the determinant of b. So to solve the equation for a non-zero vector, we get the condition that determinant of b should be equal to 0, then only we'll get a non-trivial solution. When b is not equal to 0 and x is a non-zero vector, then for the system of equation to have a non-zero solution, determinant of b should be equal to 0. This is a very important property. This is called as the determinant of b is equal to 0. Now if we summarize the whole concept, we can say that eigenvalues of only a square matrix can be calculated. Eigenvalues can be 0, but eigenvectors by definition cannot be a 0 vector. Because eigenvalues can be 0 but eigenvectors by definition cannot be 0, what does this mean? That eigenvectors needs to have some length to undergo some transformation. Third property which we will see is eigenvalues of a diagonal matrix are the entries of a diagonal. Now this is the property which we just saw in the case, in this case when one of the entry was 0, and in this case where one of the entry was 0, we saw that the eigenvalues were the diagonal entries. Now this is the same property. Eigenvalues of a diagonal matrix are the entries of the diagonal. Here the matrix A has the entries 3 and 5, therefore the eigenvalues will be 3 and 5. You can solve the equation and find out for yourself. The fourth property is maximum number of eigenvalues a matrix can have is the dimension of that matrix. So if the matrix is, we know that a matrix is a square matrix, therefore if the square matrix is 3-dimensional, then it can have at the most 3 eigenvalues. And this is a very important property. A matrix is fully diagonalizable if it has n linearly independent eigenvectors. Eigenvalues can be repeated, but eigenvectors have to be completely linearly independent for a matrix to be diagonalizable. So this is all about eigenvalues and eigenvectors. If you like this video, please like, share and subscribe. Also let me know in the comments what more do you want to learn about eigenvalues and eigenvectors. Thank you.